This video is very important to understand how slope of secant approaches the slope of tangent as we bring 2 points very close to one another. So have a good look at this video and try to understand the concept. Consider the function f of x equals to x squared. Determine an expression for the slope of the secant pq through the point P 2, 4 and Q 2 plus h, f of 2 plus h. Explain how this expression can be used to estimate the slope of the tangent to parabola at x equals to 2. So this is a very basic question and we will extend this definition for all the functions. Now here let's first try to find slope of the secant. Now slope, as you know, is change in y values over change in x value. So slope is delta y over delta x. Now in this particular equation we see the change in y values will be, let's say this is x1 y1, this is x2 y2. So it is like y2 minus y1 divided by x2 minus x1. So we can write this as f of 2 plus h minus 4 divided by 2 plus h minus 2. Correct. Now what is f of 2 plus h? F of 2 plus h is value of the given function at x equals to 2 plus h. So let's substitute x as 2 plus h and find this value. So this value is 2 plus h whole square minus 4, right? So 2 plus h whole square is this value, f of 2 plus h minus 4 divided by 2 plus h minus 2 gives us h. So we get this expression. Now this can be simplified. Let's expand this. So we get 2 square, which is 4, plus 2 times h plus h square minus 4 over h, right? And this is 4 minus 4 is 0. So we're left with 2h plus h over h. Now we can take h common. So we get h 2 plus 1. So this was h square, I'm sorry. So when you expand this, 2 plus h whole square, you get a square plus 2ab plus b square, right? So it is h square. And this is h square. So when you take h common, you get 2 plus h. This is not 2, right? Over h. So this is h times 2 plus h over h. Now h and h cancel out and we are left with 2 plus h. So from here we get that the secant at point P, which is 2, 4, so from here we get that the secant or slope of the secant PQ through these two given points is 2 plus h, right? So that is the expression for the secant. The second part of the question is, so that's the first part which we just did, and that's the second part. Let's look into the part 2. Explain how this expression can be used to estimate the slope of the tangent to parabola at x equals to 2. So for that, let me sketch here a parabola and show you the situation. So we could sketch it as x squared. So let me just make a rough sketch here for the parabola, right? And let's say the point 2 and 2 plus h, let's say p and q are points, so that we get a secant which is kind of like this. Okay, so it's not a very straight line, but I think you get the idea. So this point is p for us and this point is q for us, right? Now point p is at x equals to 2 and point q is at 2 plus h. P is at x equals to 2. So these are the 2 points and we found slope of the secant, this particular line, is 2 plus h. So it really depends on how far q is, that h value, right? So that h value is how far q is from p, right? The x value. So if we bring q closer, that means what we can do is we can find slopes for different values of h. You see? So h could be 1. So let's make kind of a table. So I'm just sketching. We'll make a table here to understand this concept, right? So for different values of h, so we'll have, we know the slope m is, so we know m equals to 2 plus h, right? And here we'll write down different values of h. So if I write h as 1, then my answer will be 2 plus 1. So I get 3 as the slope. If let's say this is the point 3, right? Now if I bring q closer, that means h is smaller than 1. Let's say it is 0.5. In that case, my slope will be 2 plus 0.5. So I can write this as 2.5. Now let me bring this q further closer. Let's say it's just 0.1 away. So this is 0.1. So my slope will now be 2.1, right? So it will be 2.1. If I bring it further closer, let's say it's 0.01, then the slope will be 2.01. And if I continue this process, what happens? Let's say 0.001, let's say. Then in that case, it will be 2.001. Do you see that? So what we see here is, as we bring q closer and closer to p, the secant approaches, the slope of the secant approaches 2. Do you see that? And as far as this line is concerned, it approaches tangent. It becomes kind of like this. When q becomes very, very close to p, then secant approaches tangent. Do you see that? So let's say this is a tangent line. Let's call this as a tangent. And what is happening, and this is our first secant to start with. So what we notice here is slope of secant approaches slope of tangent as, let me push it a bit up, as q approaches p, that is, as h approaches 0. Do you see that? So h becomes smaller and smaller. So h is from 1 became 0.5, 0.1, 0.01, 0.001, and so on. And what's happening to the slope of the secant? So m is the slope of the secant. It is approaching the value 2, and 2 is the slope of the tangent. Do you understand? So from here, what we can say, that in this expression, if h approaches 0, then slope of the secant approaches slope of the tangent, right? So if I do slight modification to all what we have done so far, that is, if I say limit that h approaches 0, then what happens? Then this slope of the secant approaches slope of the tangent, right? If I add this everywhere, and at the end, if I say limit h approaches 0, so when h approaches 0, the slope will approach 2. Do you see that? That's what we see here. So as h approaches 0, this difference quotient, which normally gives you slope of the secant, will represent approximately slope of the tangent. So that is what we learned from this particular exercise. And this is the definition which we are going to use for all our calculations of instantaneous rate of change or finding slope of the tangent, correct? So remember, let me write this definition clearly in a spot which really I don't have on this page. So let me write it here. So slope for a tangent will now be calculated by limit h approaches 0, and if we are calculating at a particular point, then it will be f of a plus h minus f of a over h, where h is approaching 0. So this expression will give us slope of tangent for any function at any given point x equals to a. You see that? So that is what we understand from this example, and it can be extended to any function. And now we are going to do many examples taking up different kinds of functions: quadratic functions, exponential functions, reciprocal functions, rational functions, cubic functions, polynomials, many different examples, and square root function, right? So we'll consider all those kinds of examples and see how to find slope of a tangent at any point given those functions. So that is what is chapter 1 for us in calculus. Thank you and all the best.